Geometry friends, here we are, still in chapter 4. We're looking at lesson 4.2. We're going to talk about angles of triangles. Vocabulary today starts off with the idea of auxiliary lines. An auxiliary line is an additional line that's drawn in a figure that helps you sometimes analyze a figure. So you might have, let's say, a triangle like this, and you see this base line here, this base of the triangle. I can draw an auxiliary line up here going through, let's call this point A of the triangle, and I can say, hey, this auxiliary line is parallel to the base of the triangle, because there exists some line that can be doing that. So I'm going to put that in my picture to help discuss something about my triangle. So an auxiliary line is an additional line or additional part of a drawing that might be added with constraints. Like, so I can't just say this line up here is the same as this line. No, I can't do that, but I can say that there exists a line that's parallel. So I can add constraints and say, hey, well, I'm going to make this line such that it's parallel. Cool beans? Hopefully that makes sense. The next thing we're going to talk about is an exterior angle. Exterior angle is best represented when you have like a polygon. I'm going to draw, I don't know, what is this going to be? A five-sided figure. We remember that's called a pentagon. So I've drawn this pentagon and I'm going to draw an exterior angle. To draw an exterior angle, you extend one side and you pull it out like that. And the angle that is created is called an exterior angle. This is an exterior angle. You guys remember that these green ones in here are interior angles, right? So these guys are interior angles. An exterior angle is created, and you can create several exterior angles by extending one side of the polygon, and then the angle that is created with the other side is the exterior angle. So I'm gonna actually highlight that in green so it could make sense. So that right there, my friends, is an exterior angle. The next thing we need to discuss is remote interior angles. So this is a little weird, but remote interior angles are specific to triangles. When we talk about triangles, you'll hear about remote interior angles. So that's why we're talking about all these angles here. If I extend this side of the triangle here, you know that I've created an exterior angle, right? We talked about that before. This guy would be an exterior angle. So the remote interior angle part comes when we think about what these angles are that are far away from it. So they are interior angles, but they are remote in reference to it not being close to this exterior angle. I'm gonna say it again because I know it sounds crazy. Remote interior angles specific to triangles refer to the other angles inside that are interior of the triangle that are not close to an exterior angle, a particular exterior angle. So let's call this, let me use a pen with a dark color. Let's call this, I don't know, like C. Let's call this C, and let's call this A, and let's call this D over here, and let's call this B. So what I want to say is that angle ACD has as remote interior angles to it angle CAB, or angle A, and angle ABC, or just angle B. Does that make sense? These are remote interior because it's remote, far away, and interior. Okay. A flow proof is actually a new term that I did not know about, and I'm going to save that definition of that until a little bit later because they have a flow proof as an example. So flow proof is, I'm going to say a little bit of what it is, but I think you can see it better a little bit later. A flow proof is kind of like, instead of having a 2-column proof or a paragraph proof, you've got this proof where you basically use arrows to talk about what you're doing. So you might say, given ABC is a triangle. And then you might say, therefore, you know, these angles add up to this, and you might have, and then eventually all your arrows, I know I'm not helping, all your arrows end up coming and explain and being, you're proving the thing is down at the bottom. Like your arrows lead up to that. So it kind of flows in a different way. Like I said, this is new to me. I've never used it in all my years of teaching geometry. So I think this text kind of created it. It's kind of dope. It's another way of thinking, and I like it because it adds kind of graphic organizers to the idea of proofs, which, you know, a lot of people have difficulty with. Finally, We're going to talk about a corollary, and a corollary is really just a theorem that is like super easy to prove as a result of another theorem. So really a corollary is just a theorem that's really easy to prove because of the proof of another theorem. I mean, that's really it. So really a corollary is a theorem. All right. So with that in mind, let's go ahead and chit chat about some examples, or let's look at some more information. Here is this theorem that I thought we already had kind of covered because it's one of those things that that I think I've taken for granted in life. That each angle of a triangle, if you take the interior angle sum, and I think I said this in the last video, thinking that we already discussed it. If you take each of these angles of the triangle and you add them up, I guess I should use blue for that one. If we take each of the angles and we add them up, it's always 180, which is kind of dope, right? Like when you think about it. The proof is not here, so I'll talk a little bit about, I'll do like a loose look at the proof. So here's how you can talk about it. So if you have a triangle like this, and do you remember we were talking about auxiliary lines? And I was like, oh, if you put an auxiliary line parallel to like the base. Auxiliary lines aren't always parallel. They can be perpendicular. They can be extended. You can pull it out and all kinds of stuff. But this particular auxiliary line to help me out is going to be parallel, right? And so we remember parallel lines cut by a transversal. So I can look at this line as a transversal, right? Remember that? And you remember that if I had that situation, then I know that the alternate interior angles are equivalent. You see where I'm going with this. Maybe you don't, but I think you're going to like it. It's dope. And then over here, we have this guy can be considered an auxiliary line. And again, I got this idea that, remember, alternate interior angles are equivalent. If lines are parallel, alternate interior angles are equivalent. We're about to get there. And then this angle right here is just itself. So look at what we just did. Angle A, okay, let's call this angle A. I'm just going to mock the picture we have here. Angle A, angle B, angle C, and angle B right here. Angle A, B, and C are also up here. And you know that this forms a straight line, right? Because these are linear. This is like a linear group of angles, right? These are linear. It's not a linear pair because it's three of them, but you get what I'm saying. 1, 2, 3 adds up to 180. Therefore, 1, 2, 3 have to add up to 180. Kind of a slick little proof, right? It was a little chatting proof. It wasn't like a real proof. Anyway, my long story short is go ahead and look in your textbook. There is a really nice proof. I'm not sure if they flow proofed on this one, but it's a good proof regardless. Take a look at it, please, 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 because I'm expecting that you can do that, replicate the proof. So I didn't do it, but I'm expecting you can replicate it like on a test or something. All right? Okay, so let's go ahead and look at our first example. The diagram shows the path of the ball and passing drill created by 4 friends. Find the measure of each numbered angle. And so remember, we've got that idea that any triangle is going to add up, the interior angles of any triangle will add up to 180 degrees. So this should be simple. We would do 20 plus, let's look at this triangle here, triangle ABC. We're going to add up 20 plus 78 plus some value is going to give me 180. Here this is written out specific for our situation here. The measure of angle A plus the measure of angle ACB plus the measure of angle B right here is equal to 180 degrees. And I did ACB because C has it's like the vertex of a couple angles. So that's why I wanted to specify I was talking about this bad boy. So what I'll do is I will simply replace them, right, with the numerical values that are given. This is 20 degrees, 78 degrees. And this is angle 3, which is what we're looking for. So I'll just put the measure of angle 3 or angle 3 there is equal to 180. Let me write that instead. So we got 20 plus 78 is going to give me 98. Plus the measure of angle 3 is going to give me 180. And if I subtract that 98 from both sides, you guys know how this goes. I'm going to end up with 82. Is equal to the measure of angle 3. So then I can go back and I can put that right into my picture, 82, and then now I've got all the information. I've got this triangle solved for its angles. Now I need to check out this bad boy, and you might feel comfortable. Oh my gosh, it's got 2 angles we don't know about. So the measure of angle E plus the measure of angle ECD, E plus the measure of angle ECD, And plus the measure of angle D has to equal 180. But what to do? Angle 2, angle 1. I hope so. I hope one of you is out there saying, come on, Miss D. You know that this is 78 and this has to be 78 because they're vertical angles. And I'm applauding you in my heart and I'm saying, yes, baby, you know stuff. Okay, so I'm going to replace what we know. I'm going to replace things with what we know. So I know that this is 61, right? And from that vertical angle situation that one of you just talked about, I would know that this angle is the same angle 2, or angle ECD as I'm calling it, is also 78. And therefore I only have to solve for angle D, or the measure of angle 1. And that's not going to be too bad for us, right? So I'm going to add up what I got. 61 plus 78 is going to be 139. Plus the measure of angle 1 is going to equal 180. When I subtract that 139 from both sides, I've realized that the measure of angle 1 is equal to 41 degrees. And so I can rock the 41 up here, and I can rock the 78 up here, and I'm done. All right, not too bad. I think that there's also a proof for this in your textbook, so I want you to take a look at it. This is called the exterior angle theorem, and so the exterior angle theorem says if you have an exterior angle, then the exterior angle is equal to the sum of the remote interior angles. Remember how long I tried to explain remote interior angles? This was why, so it kind of makes a little bit of sense. So here's our exterior angle that I'm highlighting in green. It is equal to the sum of the remote interior angles, the two angles that are far away from it, that's remote from that, right? All right, got it. All right, so the measure of an exterior angle of a triangle is equal to the sum of the measures of the two remote interior angles. So measure of angle 1 is equal to the measure of angle A plus the measure of angle B. I know that you guys are not satisfied with just hearing that. You're like, what? I don't know if I believe that. That sounds like witchcraft. If you think about it, this angle here, angle 1, and this little angle here, you know that when you add them up, they give you what? 180. Yeah. So if I add up this angle plus this angle, just looking right here, because this is a straight angle situation, this is 180. What happens when I add up this angle in here plus these three angles? Well, we just played with the fact that theorem 4.1, said that, well, the sum of the interior angles of a triangle is 180 degrees. Let's say that again. These two add up to 180. These three add up to 180. What do these two equations have in common that I just made? These two and then these three. They both have this little bitty angle in common. And therefore, this angle plus that is 180. This same angle plus that is 180. It makes sense that this green angle is equal to these purple angles. I'm trying not to do all of the work for you. Look at the proof that they have in the text. I think you will enjoy it. So here is our real world example. So we've got this person doing some yoga. We're going to exploit the idea of exterior angle theorem. Let's talk about it. Find the measure of JKL in the triangle pose. So we got JKL in this situation. All right, so triangle pose, we see it, pretty cool. We remember we just talked about this angle being equal to the sum of these two angles in here, right? So if that's the case, we're just going to set up the equation. So 2x minus 15 is equal to x plus 50. And when I do that, I'm going to just get this pretty basic algebra problem that we know how to solve. Add 15 to both sides. Move the x over here. So, well, I'll do one thing at a time. I have this guy, and then when I move this guy over here, I have x, because I'm just subtracting the x. I've got just x is equal to 65, and it looks like I'm not done, but I'm almost there. I know that x is equal to 65. I'll plug it back in here. 2 times 65 is 130, I think it is. Maybe I could be making it up. So 2 times 65 is 130. 130 minus 15 is 115. So the measure, this is the answer, I'll underline it. The measure of that angle JKL is 115 degrees. With that in mind, I look forward to talking to you guys soon. Let me know if there's any questions, and we'll get together soon. Take care. Bye-bye.